Hi, welcome to lesson 8.3, Properties of Planes. We're going to continue working on our work with Cartesian vectors to form lines and planes. And in the last couple sections, we looked at the vector, parametric, and symmetric equations of lines. And we also then looked at vector and parametric equations of planes. Now we're going to be shifting over to another type of equation of a plane. We'll start by examining properties of planes with looking at the direction vectors of planes. So a plane of space has to be defined by two non-parallel direction vectors. The cross product of those two vectors would yield the normal to the plane. So if we have some sort of plane and we've got two direction vectors, and I'll just put them tail to tail for now, then the normal to that is going to be perpendicular to, first of all, both of the direction vectors, and hence is going to be normal and perpendicular or orthogonal to the plane itself. So the normal can be used to find the scalar, or also what's called the Cartesian equation of the plane. Just like we have the scalar equation of a line, we can have now a scalar equation of a plane. So here we have an example where we've got the vector equation of a plane, and we want to find the normal of this. So we've got the two direction vectors. Here's perhaps direction vector d1, direction vector d2, and in order to find the normal, well, we know the cross product will give us the normal. So if we take the cross product of those two direction vectors, we're going to get the normal vector. And so I'll just write this out in this manner so that I can do that calculation without having to memorize the formula. So there's both direction vectors written out one after another twice. And I'm going to take the down products and I'm going to subtract the up products from those. So I'm going to have 0 minus -6 minus and 5 minus. And then I take the up products and I'm going to be subtracting those. So minus -10 is going to be, well, I'll put that -10 in there like that. And then minus 0, and then 5 minus 0 again. So then the actual normal vector then is going to be 10, -6, and 5. Okay, so therefore the normal, as we were looking for, is just that. So now, how can we tell that a normal to a plane is perpendicular to not just the two direction vectors, but to every vector in the plane? First of all, we have to show that the two direction vectors can be used to form all other vectors in the plane. And then after we do that, we're going to need to perform a simple check to show that the normal is perpendicular to all of the vectors in the plane. So for the two vectors in example 1 above, any vector v can be written as a linear combination of the two vectors in the plane. And it can look like this. So some vector is a scalar multiple of one direction vector plus a scalar multiplied by the second direction vector. And we know that P and Q are scalars. So by multiplying vector 1, 0, negative 2 by p. Depending on the value of p, that would either lengthen or shorten this vector. And the same thing would happen with q multiplied by 3, 5, and 0. It could either lengthen or shorten that vector. And when we're adding the two together, remember we're adding vectors and we add them head to tail, and then that will give us the resultant vector. So this could be direction vector 1, for example, and this is direction vector 2. When we add the two together, we get some resultant, and scalar p would lengthen or shorten or turn this vector around, vector d1, and vector q will lengthen or shorten or turn vector d2 around, thus giving us infinite number of resultant vectors if we were to try to generate every single vector on the plane. Okay, so we could do that with this formula and different values of p and q. Okay, now to show that the normal is perpendicular to every vector v in the plane, we have to show that the dot product is 0. Therefore indicating that the normal is indeed perpendicular to every vector in the plane. Okay, so we've set up the dot product here. Here's the normal, vector n, and here's vector v, which we've written up here. And now these things need square brackets because these are vectors. Okay, so these are the direction vectors on the plane. And we just have to then use the distributive property with the dot product. So we're going to have scalar p multiplied by 1, 0, negative 2, dot 10, negative 6, 5. And then we're going to have scalar q multiplied by 3, 5, 0, dot 10, negative 6, and 5. And then we can just do the dot product with each of those. So it's going to be p, and then 1 times 10 is 10, plus 0 times negative 6 is 0, plus negative 2 times 5, which is negative 10. And then we've got q, and then 3 times 10 is 30. 5 times negative 6 is negative 30. Oops. And then 0 times 5 is 0. So we see this is p multiplied by 0 plus q multiplied by 0 equals 0. So by looking at this and by examining this line, we can see that no matter what values p and q are, it's still going to turn out to be 0. Therefore, the normal vector is indeed perpendicular to every vector on the plane. We want to find the scalar equation of the plane containing all these points. So the first thing we're going to do is we're going to try to, or we're going to find the direction vectors on the plane, just like we had in the first example. And then after we have those direction vectors, we're going to then find the normal by taking the cross product of those direction vectors. So we could find vector AB, we could find AC, or we could find BC, or the reciprocals of those, BA, CA, or CB. I usually try to get them tail to tail. So I usually use AB and AC for my vectors. So I'm going to have 0 minus 1 is negative 1, 5 minus 3 is 2, and then 2 minus 0 is 2. And then for vector AC, so here's the second direction vector on the plane. So 3 minus 1 is 2, 4 minus 3 is 1, and negative 2 minus 0 is negative 2. So then the cross product is going to give us the normal. And I'll just write these out in this short form that I learned many years ago. And we'll take the down products, and that gives us -4 minus 4 minus -1 minus, and we'll subtract the up products. And so we've got 2, and there's again another 2, and then 4. So the normal to this plane is going to be -6 to -5. So now that we have the normal to the plane, we can now take the dot product of the normal with a vector p naught p, and because they're perpendicular to each other, the dot product, of course, would be 0. And so we can take a specific point, p naught, and the general point, p, and the general point is x, y, z. And the specific point, p naught, in this case, would be 1, 3, 0. And we can form a vector between those 2 points, and that would be x minus 1, y minus 3, and z minus 0. And just to reiterate that, p naught is 1, 3, 0. And general point P is x, y, z. So to get the vector between those two, we just subtract the components of point P naught from the components of P, general point P. So it'd be x minus 1, y minus 3, and z minus 0. So that forms a vector on the plane. We take the dot product with the normal, -6 to -5. And because it's perpendicular, we set that equal to 0. And then by working this, taking the dot product here, we will then find the equation of the plane. So the dot product, we take the x components, multiply them together. Then we take the y components, multiply them together. And then we take the z components and multiply those together and simplify. So we got -6x plus 6 plus 2y minus 6 minus 5z equals 0. Then we can simplify all this together. So you get -6x plus 2y minus 5z. And 6 minus 6 is 0. So that equals 0. So therefore, that is the scalar equation of the plane. Now, like we've done with scalar equation of lines, what we could do is we know that the coefficients of x, y, and z are the components of the normal vector. So we know those are going to be the coefficients. So we can just set up the general form of the equation of the line, the plane, as -6x plus 2y minus 5z plus d equals 0. And then we can substitute in a point that we know is on the plane, and that point will satisfy this equation. So I'll just take this point p naught, 1, 3, 0, and substitute these components into the variables and solve for d. So I got -6 plus 6 minus 0 plus d. And as we can probably imagine, d then equals 0. So the equation of the plane then is -6x plus 2y minus 5z equals 0. Okay, so those are two different ways of finding the Cartesian equation of the plane. Now we have two vector equations of planes, and we want to determine if these following planes, these two pairs, or this pair of planes, are parallel and distinct. So if we've got one plane here and another plane that's parallel to that, but down below perhaps, or above, they're parallel and distinct. There's two different planes. Coincident would mean that the two planes are actually the same plane. Or another way of writing that would be that these two equations represent the same plane, or neither. Meaning, and if I can draw this, which I'm not sure I will be able to, if they intersect in some manner. Something like that. Okay, so they're kind of intersecting there. That would be the neither case of this scenario. So the first thing we want to do with this is it's too difficult to determine if they're parallel or coincident or whatnot if we have the vector equations, because we've got these direction vectors for plane one. This is how we write planes in vectors with a pi symbol, whereas we know in the past we'd use L for a line. So we're using pi for the plane. So pi 1 has direction vector 3, 1, negative 1, and 4, 1, negative 4. But that doesn't mean that those are the only vectors on the plane. Of course, there are infinite number of vectors on the plane. And for us to then try to compare those vectors with the vectors of plane 2 would be very challenging. However, one thing that we would know is that a plane, if they're parallel, their normals are going to be parallel as well. They'll be scalar multiples of each other. And doesn't matter where that normal is situated. It could be over here. It could be over here. It could be down here. If they're normal to the plane, it's normal everywhere on the plane. So we only need one normal in order to compare it to the normal of the other plane. So we'll find the normals of both pi 1 and pi 2, plane 1 and 2, and then we'll compare those and see if they're parallel or not. So we're going to compare to see if the two normals are scalar multiples of each other. If they are, then the two planes are parallel. And also, if that constant that we looked at, we were like finding constant d in the last example, if the two constants of the two scalar equations are also equated by that same scalar multiple that we saw up here with the normals, then the two planes are coincident. And if, however, the planes are parallel and this k and the scalar multiple is not the same value as with the normals, then they're parallel and distinct. Okay, so we'll take a look at these and see how these can work. So actually, I'm going to ask you to pause the video for a second here, please, and work out the normals. I don't want to do the whole thing in live time for you because that'll take a lot of time. But why don't you pause the video, find the normals, and then check back here to make sure that you have done it correctly, and maybe even check if I've made a mistake, which I hopefully will not. Okay, so now that you've had a chance to take a look at this problem and determine the scalar equations, I'll just kind of go through and just double check that everything is correct on my end and yours. So for plane 1, we take the cross product of the two direction vectors. And so I set it up this way, 3, 1, negative 1, I've written out twice, and then 4, 1, negative 4 written out twice. I find the cross product by taking the down products and subtracting the up products. And then I get this normal vector, negative 3, 8, negative 1. I'll do the same thing for pi 2, plane 2, and I'll take direction vectors 3 and 4, take the cross product of those to find the normal vector of plane 2, which ends up being 6, 20, negative 8. Then I'll substitute those into the normal vectors as the coefficients of the plane and leave D1 and D2 over here to be solved for. And then when we work all that out, d1 is 15 and d2 is 8. So then the actual scalar equations are, as you see here and here. And if we look at the coefficients, we've got -3, 8, and -1. And over here, we've got 6, 20, and -8. And we can tell by that that definitely the two normals are not scalar multiples of each other. Therefore, the two planes are not parallel. Therefore, the two planes are, from what it says above, are neither. In other words, they do intersect. They're not parallel, and they're not coincident. And actually, they would intersect in a line that's actually more accurate. We'll get into that a little bit later, because basically two coincident planes are intersecting, and their intersection is an entire plane. And a couple other examples of planes in space. So we've got plane 1 and plane 2 here. We can take a look at the coefficients. So these would be the normals. The normal of plane 1 is 3, 4, -5, and the normal of plane 2 is -6, -8, 10. Upon closer examination, we can see that normal of plane 1 is equal to -1/2 the normal of plane 2. So that indicates that the two planes are parallel. We see that when we compare the two constants, d1 is equal to -1/2 d2. And because they have the same scalar, that would equate the normals, that would also equate the constants. That means that the two planes are coincident. If we look over here for these other two planes, we basically got the same normals, 3, 4, -5, and -6, -8, 10. We see again that the two planes are parallel because normal vector 1 is equal to -1/2 normal vector 2. But then when we compare the constants, -5 and 15, we see that d1 is -5 and d2 is 15. d1 is equal to -1/3 d2. So they are scalar multiples, but it's a different scalar multiple than were the normals. Thus, the planes are parallel and distinct. Okay, and so that wraps up our work from section 8.3, Properties of Planes. So thanks for watching, and we'll see you in class.